Good morning, everyone. Today I am going to give a final project presentations. My project topic is design and analysis of vehicle to grid and grid to vehicle technology for electric vehicle. We are two members in our project group. My name is Asiswara and my other colleague is Collins. Our supervisor name is Dr. Ashraf Ali Khan. This is the content of our project: introduction, abstract, problem statement, objectives, methodology, block diagram, circuit diagram, simulations and results, conclusion and future work. This is the introduction of our project. Vehicle to grid and grid to vehicle are cutting edge technologies revolutioning the landscape of electric vehicles. Vehicle to grid empowers electric vehicles not just as energy consumers but as contributors to the grid, allowing them to discharge excessive energy during low demand periods. On the flip side, G2V enables electric vehicle to intelligently charge from the grid, ensuring optimal energy utilization. This bidirectional power operation not only enhance the grid stability but also play a pivotal role in promoting sustainable energy practice and fostering a more dynamic and resilient energy ecosystem. Additionally, the investigation extends to the incorporation of vehicle to grid and grid to vehicle technology in electric vehicle charging stations. The abstract explores the transformative concept of vehicle to grid and grid to vehicle operation in the realm of electric vehicles. Vehicle to grid enables electric vehicle to contribute surplus energy back to the grid during peak of time, enhancing grid stability. Conversely, grid to vehicle facilitates intelligent charging from the grid, ensuring optimal energy utilization to the vehicle. This bidirectional integration not only bolstered grid resilience but also underscored the role of electric vehicle actively participate in sustainable paradigm. This abstract relieves the pivotal impact of this operational on reshaping energy dynamics and fostering a more adaptive and eco-friendly transportation system. Also, the performance assessment of the vehicle-to-grid system involves evaluation of the transfer efficiency, battery life impact, and responsive to grid. Potential benefits including improved integrity of renewable, decreased transmission losses, and enhanced grid stability. So now I am going to talk about the problem statement. Challenges in bidirectional power flow efficiency, standardized solutions for diverse electric vehicle models, and concerns about the battery health in vehicle to grid system required innovation approach to design seamless and adaptable solution for electric vehicle charging solution. Also, key issue including the needs for seamless bidirectional energy flow integration, grid compatibility, and infrastructure development. Additionally, the statement highlights the potential obstacles such as the standardization, regulatory framework, and user acceptance. Solving these challenges is crucial for unlocking the full potential of V2G and G2V, thereby advancing the transitions to a more sustainable and grid-responsible electric vehicle ecosystem. The economic viability of vehicle-to-grid and grid-to-vehicle technologies necessitates careful consideration of factors like potential revenue streams, operating cost, and initial capital investment, urging a comprehensive exploration of these complexities for informed decision making. By addressing these technical, governmental, and economic challenges, research aims to pave the way for a resilient and sustainable electrical ecosystem, leveraging the advantages of electric vehicle while ensuring integration into broader electrical energy range system. The primary objective is to optimize bidirectional energy flow, enhancing overall energy management. The study aims to assess the financial viability of developing V2G and G2V technologies, exploring the revenue stream from the grid-linked electric vehicle service like a frequency management and peak saving. The project addressed large-scale V2G integration challenges, evaluating its impact on grid resilience and facility. Here I am going to talk about some objectives for the grid standard stabilizations is enables electric vehicle to act as a grid assets by providing vehicle to grid supports during peak demand and enhancing grid stability and reliability. Apart from that, optimize charging. Implement G2V to allow electric vehicle to intelligently charge from grid during low demands, and it's also optimize energy consumption and its cost. Renewable energy integration. Facilitating the integration of renewable energy sources by using electric vehicle storage units, mitigation intermittency challenges throughout the V2G supports. Also, consumer education. Educated electric vehicle users of the benefits vehicle to grid and G2G, promoting awareness and acceptance of bidirectional energy flow technology. Moreover, access the quality and quantity of the environmental impact V2G and G2V operation, emphasizing reduction in carbon emission and overall environmental sustainability. So, by achieving these objectives, the integration V2G and G2V operation aims to create a more resilient, sustainable, and efficient electric vehicle system. So, that is our main objective of this project. Here I am going to talk about the methodology. The solar PV electric vehicles charging station design begins with the calculating total solar PV capacity based on the site space and anticipate energy consumption, followed by determining the quantity and power of solar panel required. So we need for the electric vehicle power system like input and output, that can be input is provided by the grid or renewable energy sources. Output is for the propulsions on onboard system. After then, bidirectional converter. Function for the converter power like AC to DC to facilitate the bidirectional energy flow. Operation during V2G converts DC power from the electric vehicle's battery to AC for grid injection. During grid to vehicle converts AC power from the grid to DC, and it's help to the electric vehicle battery. Also, energy management system helps to monitoring the energy demands, grid condition, and user interface. Vehicle control units help in our system is to integration, coordinate communication between the electric vehicles component and electric uh, me- uh, electric vehicle system. Monitors battery condition to ensure the bidirectional power flow exchange. Also, circuit breakers and fuse helps to the overprotection control, and grid tied inverters transport DC solar power into AC to DC charging, integration of electric vehicle charging approaches including DC fast charging ensures the compatibilities with the inverter power requirements. Moreover, designing the bidirectional grid connection adheres to regional law, verifying protection and grounding system for proper grid interconnections. We use a software to install and manage charge schedule based on the grid pricing and solar power availability. Also, we plan for the maintenance and ensuring the system runs as per the time schedule. Troubleshooting features are incorporated to facilitate promote issue resolution and charging station operation efficiency. Our methodology aims to create solar PV EV charging station that's compiled with the electrical standards, safety regulation, and optimization solar energy harvesting. Evolution of grid-to-vehicle technologies adaptability to models and charging specification is conducted through simulations providing critical insights for the successful integration of vehicle-to-grid and grid-to-vehicle technologies in electric vehicle charging station. So this is the block diagram of our system. The block diagram for the G2V and V2D system, which also serve the conceptual basic for the working system, and it's help to maintain the technological, financial, and regulatory aspects. So electric vehicle with the bidirectional inverter commutes with the grid controller. So we use a different system here like electric power system input and output. So input get from the grid and output is help for the onboard system. Bidirectional converter function is used for the AC to DC and DC to AC whenever it's required for the system. We use the energy management system to monitoring the our energy demand and grids related to all the system. After that, we use a grid interference to connect the link electric vehicle to external power grid. So communication facilitates data exchange between electric vehicle and grid operator. So this is the vehicle to grid and grid to vehicle framework development block diagram. Here you can see the energy sources, inverter, charging station, electric vehicle, photovoltaic array, and G2V and V2G function. So that's also help into renewable energy integration. That's the renewable energy sources like solar or power that contributes to electric vehicle use contribute renewable energy to the grid during V2G. We use here user interface that provide information on charging status, energy prices, and grid interconnections. So control allows user to set preference and schedule for the charging and discharging. So the PV is work as a grid. So they provide the energy to our system. Like we get energy from the grid to the electric vehicle, and electric vehicle is use that energy to for their transportation purpose. So whenever the electric energy, that's the store in our electric vehicle. So that's the excessive energy we can send it back to the charging station or battery. So whenever that's need, so we can use that again, and we also share that the electric energy to the commercial purpose. So that's the function of the vehicle to grid and grid to vehicle. We explain in our this the block diagram. Apart from that, there's the bidirectional communications inverter enabling power flow and grid interference ensuring integration stability. In that the G2V framework, the grid interference connect to the charging station. As I mentioned earlier, charging station control optimization, power delivery, electric vehicle interference enables communication with the electric vehicle, shared the components, encompass standardized communication protocol, security measures, and grid service integration for data security and grid support service. So this is the use for the vehicle to grid and grid to vehicle framework. We mostly use this system to implement this our in a circuit diagram as well as that's implement in our MATLAB simulation, and we take the output. So we take discuss in further parts. My other colleagues will explain more from next slides. Thank you.
To continue the presentation, I want to talk about the circuit diagram of solar PV EV charging station with the grid. And this circuit diagram was designed after our MATLAB simulation, and this design aims to maximize the utilization of renewable energy sources while providing a bidirectional energy flow capacity to support both the charging needs of EVs and the grid stability through V2G technology. And when looking at the circuits here, you see that there's a lot of components. We have our charger controller. It controls solar panel voltage and the current to charge batteries and manage power flow. We also have our EV battery storage. This stabilizes power production and stores extra solar energy for later use. We have our bidirectional DC to DC converter. This enables EV charging G to V by converting DC electricity from the solar panel and batteries to AC power and the vice versa. We have our grid connection. This permits the charging station to feed surplus energy generated into the grid, that's V2G, and allows it to draw power from the grid when solar power is insufficient. Now, how does this circuit work? Solar panel connected in series or parallel configuration. Now connected to the charge controller to regulate the voltage and the current. Now output from the charge controller linked to battery storage system. Now the battery storage system includes a bidirectional inverter to manage power flow between the battery and the EV charging station. Now connected to the grid through a bidirectional inverter for V2G functionality. Now bidirectional inverter connected to the grid enables vehicle to grid functionality to feed SS. Okay, now we talk of the simulations and the results. The figures here are our simulations and results. This simulation shows PV voltage, current, and the power over time, fluctuating based on sunlight. Result review optimize power generation for EV charging, grid interaction, and the storage, validating V2G and the G2V efficiency in balancing energy demand while leveraging solar PV for sustainable electric vehicle infrastructure. And when looking at it, you see that the simulation runs this way. We have our PV voltage, and the voltage is started from the 0, then it increases to 400, and it keep on moving constantly to 400 volts. Then we have our PV current. Also, that one starts from 0. The simulation starts from 0, and when it gets to 8 ampere, it maintains its regulation. We also have our PV power. It also starts from 0. When it gets to 400 watts, at 0.5 seconds, it reduces. The power reduces. So we also have our EV batteries. Okay, we have our inverter voltage, inverter current, and grid current. Now the inverter voltage is, when looking at it, it started from negative 400 to positive 400 volts, and the sign is sinusoidal. This is how the simulation runs. We also have our PV power. We have our DC load power, battery power, grid power. We have our SOC storage in percentage. We have our SOC EV, battery voltage, battery current. In conclusion, this analysis emphasizes how important grid to vehicle and the vehicle to grid technologies are to the integration of EV with the grid. It creates a solid structure while addressing technological, grid stability, and economic issues. A sustainable and inventive future is presented by bidirectional power flow technologies, which open the door to a networked electric mobility infrastructure. Now, policymakers, owners of charging stations, and the other EV stakeholders can benefit from the study's insights, which will help to develop an innovative electric vehicle landscape. We also have our future works, and the future work in V2G and the G2V technology will cover user adoption, cybersecurity, grid optimization, renewables integration, tech advancements, economic models, field threats, and the regulatory aspects. Future developments in the integration of solar PV EV charging stations with the grid are anticipated to include improved and affordable solar plan. Thank you.